The Trinity nuclear test on July 16, 1945 was the first detonation of a nuclear weapon. The explosion created a blinding flash that gave birth to a colossal mushroom cloud. Shockwaves rocked the ground, sending debris miles into the sky. Radioactive fallout contaminated the environment, changing the Earth's atmosphere and surface, greatly impacting something called the geological timescale. Today, we're going off the radar to help you better understand Earth's geological timescale and the lasting impacts nuclear testing has had on that scale. We'll also look at why some experts say the scale needs to be changed. I'm meteorologist Emily Gracie, and you're listening to Off the Radar, a production of the National Weather Desk. On the show, we dig deep into topics about weather, climate, the ocean, space, and much, much more. Our goal is to help you better understand the weather and to love it as much as we do. There's no doubt this summer's blockbuster movie Oppenheimer has created renewed interest in the development of nuclear weapons. And now a group of scientists is working to prove that the timeline of Earth's history should be changed. And the reason for that change? The use and testing of atomic bombs.
The first time that there was the explosion of an atomic bomb in 1945 in the New Mexico desert was the first time that nuclear fallout fell out of the sky. So that's the marker that they started thinking about.
Dr. Francine McCarthy led a team to the discovery of a lake in Canada that best represents that geological change. I'm talking to Francine today about what led them to the lake and how the first explosion of an atomic bomb is showing up in that historical record and creating a distinction in Earth's timeline that can be seen in numerous sites worldwide. Francine is a micropaleontologist and an earth science professor at Brock University in Canada. She's going to explain how they made the discovery and why some people are adamantly opposed to the recognition of this change. Let's start at the beginning. And can you give me a little background for people who don't understand maybe geological time periods, how we structure things now, how we define things?
The geologic timescale breaks up time since the Earth has existed based on what we find in the rocks themselves. So mainly the kinds of fossils that we find. So 66 million years ago, the dinosaurs became extinct, but I think most people are kind of aware of. That marks the end of the Mesozoic era and the beginning of the Cenozoic era. So eras are big intervals of geologic time. So we're now living within the Cenozoic era, but we're within the Quaternary period of that era. And the Quaternary is basically the time since big ice sheets have been growing and melting. So glacial, interglacial changes in climate. So we see things like, mammoths and mastodons and things like that, things that are associated with the Ice Age until 12,000 years ago. And that's when the Holocene started. And according to the timescale currently, we're still living in the Holocene. And that's one of the two epochs of the Quaternary, the Pleistocene, the Holocene. So 12,000 years ago-ish, the end of the last ice age marks the beginning of the Holocene. We, the Anthropocene Working Group, propose that we're no longer in the Holocene, that we haven't been in the Holocene since the middle of the 20th century, so around 1950, that conditions are so different because of primarily greenhouse gas concentrations in the atmosphere being so much higher than they were before humans started burning a lot of fossil fuels, that there was a tipping point that occurred in the Earth systems. The way the Earth system actually behaves, the way the atmosphere and the water, the hydrosphere interacts, etc., actually is no longer the way it was behaving for 12,000 years. So in terms of Earth history, we would propose that we not think of the Earth being in a Holocene mode, but instead being in an Anthropocene mode. So if we're trying to project into the future and try to understand and predict what might be happening in 20, 50, 100 years, using the best data that is based only on the way the system works now and has worked since the mid-20th century is the way to go. So I often compare it to if you're dealing with a human being Once they become teenagers, you can't really deal with them the way you used to when they were 3 or 4 years old. If you do that, then you're not going to have any success. It's the same person, but the system is different.
Okay, so I understand how you look at dinosaurs and rocks and fossils. I'm curious how the change in what we're seeing in the atmosphere is showing up in the ground.
Yeah, so there are all sorts of physical, chemical, and biological fossil things that persist that are captured in the sediments of the earth. Anything that falls out of the atmosphere and accumulates is a kind of sediment. It records things like pollutants in the atmosphere. It records different kinds of organisms living in a lake, for instance, if you have acid rain or not acid rain. So back in the 70s and 80s, that was a big deal, right? And so different kinds of conditions in the water, in the atmosphere, all of these things are recorded by the little fossils, but also we can actually measure directly chemical changes. So changes in isotopes of things like nitrogen, which is the most common element in the atmosphere. We can measure little physical things like particles of fly ash that fall out of the atmosphere that are the particulate pollutants that are produced when you combust fossil fuels, particularly coal. So the dust that falls, the fly ash, the dust that falls back. So all of those things we can measure, and we have measured in Crawford Lake, but also at 11 other sites across the planet. And we found the same thing, that there is a major shift that happened all around the world around 1950. And that's why we feel confident in proposing that a line be drawn on that timescale that says we're no longer in the Holocene. We are now in the Anthropocene epoch of the Quaternary period.
Okay, so 11 sites around the world. How did you find these 11 sites, and what about Crawford Lake in Canada, correct?
Yeah.
What about that specific location really showed you what you needed to see?
In the year 2000, this atmospheric chemist, Nobel laureate Paul Crutzen, got up at a meeting and said, stop talking about the Earth as if we're still in the Holocene. It's the Anthropocene. It's been so altered by humans. 9 years later, in 2009, the stratigraphers, the people who control the geologic timescale, decided that word, Anthropocene, sounds a lot like Holocene and Pleistocene and all of these other epochs of geologic time. They're used differently by different people to mean different things. So they decided we have to take control of this and make sure we define it accurately, precisely, so that everybody means the same thing. Fast forward now to 2016. After 7 more years of discussion, the Anthropocene Working Group came to the conclusion that, yes, we are going to look to defining that line on the timescale the way we've defined all the other lines on the timescale, by looking at the geology of the planet, trying to find sites that are like the model that represents best that change. So by 2019, they had gotten enough funding together to actually start funding the work. And they had started to think of places that they were aware of that might have the right characteristics to be able to define such a recent interval of geologic time. If we're looking at the mid-20th century to call an end to the Holocene and the beginning of the Anthropocene, we have to be able to be really precise about where we're putting that boundary. It's not good enough to be plus or minus 1,000 years. We're looking at something that was 73 years ago. So ideally, what they were looking for were sites that had annual resolution possible. So that means that you can sample each year separately. So if you think of tree rings, for instance, most people are aware you can do that with tree rings. You can count tree rings to, count how many years the tree's been alive. But if you sample just that one ring, you have that year. So that's what we're looking for. So coral reefs are an example. There were 2 coral reefs, one in the Great Barrier Reef area of Australia and the other one in the Gulf of Mexico, that were considered, because corals have annual growth bands, and other places around the planet where these kinds of annual layers might accumulate. And lakes like Crawford Lake are unique, special lakes in that the layers that accumulate on the lake bed are seasonally distinct, so that, like tree rings, we can look at sediments in a core, taken through the lake bed, and we can actually identify the year 1950. We can identify any year you're interested in. The last 100 years, you tell me a year, and we can pick that one and sample it just that 1 year, and then we can analyze it for those chemical, physical, and biological fossil remains to see, well, what was going on in the planet that year? What was the health of the planet? What was the atmosphere like? What was the water like?
So this is very cool. And I've seen this, I've talked to several people who are doing this in the sediment cores that are, just telling history in all different ways. Yeah. But I visually, I want to know what a year looks like. What's the distance? If you're looking at 1 year, yeah. What is it, an inch? Is it a foot?
No, gosh. It's a year in Crawford Lake is about 1.5 millimeters. If you need a fairly large volume of sediment for your analysis, that means you're going to probably need a couple of years smushed together, right? It depends on how much each different kind of analysis needs. If you have enough cores, and it's easy to, a year like 1950 is easy to pick out in any core. So you can correlate from core to core to core and just pick out all the 1950s from 4 cores if you need to smush them together into one sample, right? So you can actually get annual resolution for literally anything you want as long as you have enough cores.
Okay, so 1950, you keep saying 1950, which feels very specific. Also, I'm a little confused because, we talk about the Industrial Revolution. So what is it about 1950 where this change is suddenly and clearly happening?
So at the beginning, when Crutzen, had his tantrum in that meeting in 2000, that was the assumption that it would have been at the beginning of the Industrial Revolution. And he actually suggested in one of his early papers that we could use the date that James Watts invented the steam engine as, the beginning. The thing about that is that in England, it was hundreds of years earlier than in China. Okay, so China is heavily industrialized today, but it's only been heavily industrialized since Chairman Mao died. So the hundreds of years apart of what you would see as the evidence of the Industrial Revolution in England compared to in China makes drawing one line on the time scale impossible. It's like trying to get a Zoom meeting together across time zones. You have to make sure that, we're all talking about the same time. So, and they started to look for things that were globally synchronous around the world at the same time. And one of the things that is obvious when you think about it, that falls out of the atmosphere all at the same time within a year or so, is nuclear fallout. The first time that there was the explosion of an atomic bomb in 1945 in the New Mexico desert was the first time that nuclear fallout fell out of the sky. And because of the mushroom clouds, they get into the upper atmosphere and they whiz around the world and they fall out, right? Nuclear fallout. So that's the marker that they started thinking about. They thought, well, okay, so that's something that's same time all around the world. They looked at lots of records of that time around 1945-ish, and they saw that around that time, the thing that actually happened to the Earth system, the detonation of those atomic bombs and the nuclear weapons testing of the Cold War, they didn't markedly change the way the climate system works. But what did change the way the climate system works is that great acceleration of human industry, particularly fossil fueled industry, that really ramped up with the war effort, the Second World War, and it just kept right on going. So the 1950s and 60s, that post-war boom of industrial and economic expansion, and the baby boom, the number of humans that were doing all of this just ramped up. And it became clear that around the time that we start to see nuclear fallout, we see a sudden shift in the way the Earth system responds. And that is what, in fact, Paul Crutzen had a hissy fit about years earlier, talking about we're no longer in the Holocene. Things are too different. Humans have affected the planet. He's now dead, but he was an atmospheric chemist, and the chemistry of the atmosphere is markedly different today than it was 100 years ago. And if you were to pick one year where you were going to put that line, we, Team Crawford, have suggested the year 1950 as that year, which is why I use the word 1950 a lot.
It's like a nice clean year where there's like a control.
Yeah, so it's a nice round number, which is part of it, but there's a ramping up of a huge number of things, within a couple of years. Within 2 or 3 years in the early 1950s, we see this marked change. But why 1950 and not 51 or 52 or 53? Partly it's because it's a round number, but the most important rationale we used is that, I don't know if you've ever seen radiocarbon ages reported, but if you send something out for radiocarbon dating, geologic sample or an archaeological sample or whatever, it'll come back to you from the lab and it'll tell you how many years before present it dates to. And the before present, or BP, is always relative to the year 1950. And the reason for that, so if you're actually interested in actual calendar years compared to 2023, you have to add 73 years to your age of your sample, because starting in that middle 20th century, those mushroom clouds were creating in the upper atmosphere huge amount of artificial radiocarbon. And radiocarbon is created in the upper atmosphere by bombardment of nitrogen, which is the most abundant element, when usually normal solar radiation bombards nitrogen. Some of them become carbon-14. There's a little subatomic particle that goes boing, like a billiard ball, and it becomes radiocarbon. That's the way it naturally happens. But with all of this additional radiation from mushroom clouds, all kinds of artificial radiocarbon was created. So you can't use radiocarbon ages after all that radiocarbon was artificially created, because if you do date something that's 70 years old, the date that you'll get back from the lab will be hundreds of years in the future, because the system has changed, right? I mean, the system is based on the natural background rate of creation of radiocarbon. It's not based on human-created radiocarbon being in the mix.
So now I'm curious, can you radiocarbon date something from the past 73 years? Is it accurate?
Well, no, because it'll literally will give you ages in the future. Everything since basically 1945, but certainly 1950s when the Cold War started, all of us have way more radiocarbon in our systems than our grandparents had. Because
so people in like a few hundred years aren't going to be able to look back and radiocarbon date our remaining.
Not using radiocarbon dating. No, the present for radiocarbon will always be 1950 Common Era. They will always be that.
And that's depressing.
There are other ways you can date things. Like radiocarbon isn't the only game in town. It's the one that most people are more familiar with. But yeah, radiocarbon dating is only useful up to 1950.
Wow. Okay, I didn't know that. Very interesting. Okay, so take me back to Lake Crawford. And did you go out there? How did you get these samples? Do you just take like a giant straw and jam it down into the lake? How does it work?
Yeah, the best way to preserve those annual layers is to use what we call a freeze core. And a freeze core is a metal sampler that's hollow that you fill with a slurry of dry ice and ethanol. And that brings the temperature down. I can't remember. I think it's minus 35 degrees Celsius or something. It's super, super cold. And so you then just drop this freeze core, which is quite heavy because it's metal and it's filled with all of this stuff. You drop it into the lake bed. You just drop it in. And then you leave it for half an hour and you pull it back out, and the lake is actually frozen onto it. Like you've dropped it in and it actually freezes. It's like if you put your tongue on a cold swing and it sticks there. So it actually sticks onto the side of the sampler. Basically, you bring it up as it goes through the water column, you're left with this beautiful, looks like beautiful tree rings. So we did that. I've been going to the lake since the mid-1980s, but for this Anthropocene project, we went out first in 2018 to just test to see if it would be a good site. And then between 2019 and this April of 2023, we went out and we collected a dozen cores or so.
But not everybody wants the Anthropocene. So tell me, what's the controversy and why is there controversy?
Yeah, there's a couple of reasons, quite different reasons. First of all, I think the one I sympathize with most is that since the year 2000, all kinds of people have used that word in a way that makes sense to them.
So some people aren't against it. They're just against the word.
So for instance, when I say people who made the term what it made sense to them, the fact that anthropos means human, right? Some people have used it to mean the entire time since humans have affected the planet, which is a very long time, certainly not 1950. Like people who conceive of the Anthropocene like that look at us and say, 1950, are you crazy? This is like there have been humans impacting the planet for much longer than that. So I get that. The thing is, the word Anthropocene sounds like all of those other formally defined lines on the timescale, Holocene, Pleistocene, et cetera, et cetera. So for the geologists, the stratigraphers, people who deal with geologic time, it's like, well, we either ignore the fact that this term is out there or we make it mean one thing around the world. So it's like time zones. We're not going to walk around policing people and say, you can't use that word anymore unless you mean 1950. Like, that's not the intention. But if you use the term Anthropocene and have an epoch with a capital E after it, which means formally defined, like a formal name, then we would say it has to mean the same thing, 1950 or whatever. But there are also people who I think are against the idea of having such a recent 73-year-old line on the timescale because they're used to thinking of geologic times in millions and billions of years. And so what's this 1950s crap? This is way too sudden, way too recent. And it basically is too close to politics and sociology, and most natural and physical scientists don't really like to go there. They don't want to get involved with that. So I get that. The thing is, in identifying this recent shift in the Earth system around the world, as I mentioned earlier, we the geologists, have recognized how rapidly and how dramatically the last 73 years have altered things. If you extrapolate into the future, it's like a runaway train, right? It's not slow and gradual. It is really rapid. And in having identified that that's not what we set out to do. But once it became clear that all around the world, there's evidence of this dramatic shift that means that things are changing at a rate that has not been seen in over 12,000 years in the Holocene. What interests most people who aren't just focused on the time scale is, what does it mean to us, to our future, to the future of my family, to the future of humanity in the bigger sense? And that has nothing to do with whether there's a line on the time scale. It brings us into this sort of more philosophical, quasi-political kind of discussion. I'm not against it personally. Obviously, I wouldn't be talking to you if I were. But there are a lot of people in power in that stratigraphic world, people who are going to be deciding whether there should be a line on the time scale, really don't want us to be talking about it. They see us as trying to get attention, to seek publicity. My response to that is, we are not running around seeking attention from reporters or, people from the general public people are coming to us interested in the work that we've done and recognizing the possible implications of geology for a change. People are actually noticing geology, and they're recognizing that the Earth that we're living in now isn't the Earth that our great-grandparents lived in, and that making the best decisions for the future requires that we accept that reality and we deal with it.
The Anthropogenic Working Group will present its proposal for official recognition sometime this fall to the relevant geological authorities, with a final decision expected sometime next summer. Special thanks to Dr. Francine McCarthy for her insight today. Off the Radar is a production of the National Weather Desk. Make sure you're following the show on Apple Podcasts, Spotify, or wherever you listen to podcasts. New episodes published every Tuesday. If you know someone that's interested in geology, paleoclimatology, or just loved the movie Oppenheimer, please share this episode with them. We'd also love you to rate and review us on Apple Podcasts and Spotify. Let us know what you think of the show and give me some ideas for future episodes. Special thanks to Ryan Berlin from the National Weather Desk for his help with this episode. I'm meteorologist Emily Gracie. Make it a great day.